We are Senior Design Team 10. We have been tasked by Fiat Chrysler Automobiles to create a vehicle body structure component using Pultrusion. On our team, we have myself, LeAnn Howe, Liam Munro, Kyle Sitkins, Noah Stark, and Joshua Walsh.
Our customer contact, Sean Whalen, recognized the potential benefits of a material called Pultrusion and tasked us with finding an automotive use for this material. As shown in this diagram, glass fibers are impregnated with a thermosetting resin and then passed through a heated dye to cure, resulting in a high-strength, low-mass part. Pultruded parts offer an alluring way to reduce vehicle mass, as they are a cost-comparable alternative to heavier steel and aluminum parts. As shown in these graphs, they are lighter than aluminum while being stronger than steel. Fiat Chrysler, like other auto manufacturers, has difficulty keeping up with EPA-mandated gas mileage and emissions regulations, in part due to high vehicle mass. Reducing vehicle mass through the use of lightweight pultruded parts helps increase fuel efficiency.
At the beginning of the first semester, FCA invited the team down to visit their benchmarking facility in order to get a hands-on look at what possibilities there were for choosing a part to redesign with Pultrusion. This project with FCA was open-ended, meaning that we were not restricted by FCA when determining where we could aim to reduce weight. Rather, we were only restricted by the limits of the Pultrusion manufacturing process itself. Pultrusion-produced parts are limited to constant cross-section. Manufacturing constraints also dictate that a part must be straight, have no more than 3 internal passages, and have walls between 2 and 5 millimeters thick. Pultrusions are also severely anisotropic, meaning the strength in the axial direction is much greater than in other directions.
After many rounds of decision matrices, the truck bed crossmembers proved to provide the most potential for weight savings, as there were multiple per truck. Within the yellow boxes are the chosen crossmembers. This is our final system-level concept. The pultruded I-beam is attached to the bed with structural adhesive that cures during the e-coat process. The steel brackets provide clamping force to ensure even pressure while the adhesive is curing. We chose an I-beam profile for our design in order to use the pultruded material efficiently. Our design also uses fewer spot welds, 12 as opposed to the current 42. This reduces assembly time as well as total part cost. The final design saves 57% mass, or 1 kilogram.
During the design process, we used HyperWorks to iteratively compare our concept performance against the original part. We also designed in a 1.4 times safety factor to account for the uncertainty we had in dealing with this new material. We tested both beams with a hydraulic press in the main basement. Both were slightly less stiff than what HyperWorks had predicted. Our prototype tested almost exactly 1.4 times stiffer than the original part, reflecting the 1.4 times safety factor we added during design.
We were able to meet all of our design constraints and objectives. Some of the most notable successes are shown in this table. Our part reduces mass by 57% while being both stronger and stiffer than the current part. In addition, it is cheaper to manufacture and assemble than the current crossmember. We would like to acknowledge and say thank you to the following people and companies: Sean Whalen, L&L Products, Joe Thomas, Dr. DeClerck, and Dr. Endress. Thank you.